Well, here's an application of solubility equilibria. It involves lead carbonate, which used to be used commercially as a white pigment. In fact, if you have a house that was painted white prior to 1970, there's a good chance that it was painted using a lead carbonate based paint because it was a nice paint in terms of durability, ease of use. But this has been banned because of the toxicity of lead. The only place you're getting white paint or use white paint is to use it for oil painting. And as you can see, here we've got some Kremitz white oil paint, and they warn you that it's toxic because it has lead, and it's pretty expensive, about $5 for a milliliter. But let's get on to the problem, and we'll incorporate the solubility as part of that. The question says the molar solubility of lead carbonate in water is low, 1.8 times 10 to the negative 7 molar. So in 1 liter of water, you're going to have 10 millionths of a mole of lead dissolved. That's about a speck of dust. But even then, you have to worry about it in terms of toxicity, especially for younger children. Okay, we're supposed to calculate the KSP for the lead nitrate. The KSP is based on how much of this material will end up dissolving. And we're dissolving this in water. So when we start off, we have our solid. This is the molar solubility, 1.8 times 10 to the negative 7 moles of solid lead carbonate, this white stuff. No lead ions and no carbonate ions in the water initially. The molar solubility means that you're going to lose that amount of carbonate, that speck of dust. So this is going to be a negative value as our change for the solid, but a gain for each of the products, which are lead ions, lead invisibly dissolved in water, and also the carbonate. Now, it's going to be the same value because this associates 1 to 1. So we'll have 1.8 times 10 to the negative 7 of lead ions tossed in. And also, we'll have carbonate ions. We get 2 for 1. Now, be careful with other problems if there's stoichiometry. If we had a 2 in front of here, let's say this is a lead chloride, then we'd have twice as many ions of chloride than our initial solubility. So that has to be taken care of. Something has to look out for. Now, at equilibrium, all of this lead carbonate, not much of it, speck of dust, will have dissolved in that liter of water. If you dump in more lead carbonate than this, it's not going to end up dissolving. This is the max that will dissolve in 1 liter of water, but it will give you this amount of lead and this amount of carbonate. Now we're going to use that solubility in the solubility expression because the KSP, the solubility product, because it is a product, is going to be the lead concentration times the carbonate concentration. So let's do this on a TI. Here's the TI, 1.8, second function times 10 to the negative 7, and we just have the same value again because the carbonate equals the lead in this case. So let's just hit the x squared and see what happens. There's our value, a low value that we'd expect because this has a very, very small amount of lead carbonate that will dissolve in water.